Good afternoon, everybody. Can you hear me all right? Perfect. It is such a great pleasure to be here yet again. The first time that I came to Litomyšl was in 2004, and then again 2014, and then again now in 2024. So if you don't have anybody booked for 2034, I'll volunteer for that. Alrighty. So when I was thinking what I might present that would be interesting, I was thinking that uh, most of you are probably well versed in observations, and I tried to give you a pathway towards contributing to professional science without needing anything except a computer and zeal for doing astronomy. And this is why I focused on the role of citizen science in the 21st century astronomy. So let me first define what I mean about by citizen science. So if you look at Wikipedia, this is what you'll see. That citizen science is research conducted with participation from the general public or amateur non-professional researchers or participants for science, social science, and many other areas. So the idea really is to pursue your passion, even though that might not have been your vocation that you've chosen. And the idea is that if you're an astronomer at heart, it really does not matter what you do for your bread and butter, but instead that you can still fulfill the passion and contribute meaningfully to our understanding and the studies of the universe. So I went online and was extremely pleased to find a Czech version of what's called Citizen Science Project. So several countries now have their own designated citizen science projects. So if you happen to be Czech, I heard that there are participants from 10 different countries. Well, I apologize to the participants from 9 countries, maybe 8 if I count Slovaks as someone who could easily follow Czech as well. Of course, my suggestion is check whether your own country has a dedicated page, and if not, find the one that does have it. So I went online and I saw this. I would be amiss to say that I understand everything that's written up here, but being a Slovenian myself, I can interpolate reasonably well so that if I had to, I'd be able to choose a project that's quite interesting. Now, I imagine that what we share in this room and online is passion for astronomy. So you may wonder just how many astronomy projects there are. So how much can citizen scientists actually contribute to astronomy? So here I went to the American citizen science page, and I remind you, of course, oh, sorry about that. It's just a little bit slow. That all these citizen science projects are global. You do not have to be Czech to be on the Czech citizen science or American to be on the American citizen science. In fact, we see global participation from such a wide range of nationalities that these are truly global projects. And I'm showing you here just a few, and unfortunately I'm tied to this podium, so I can't point easily. My apologies for the noise. I have to move this just a little bit so that I can see a little bit better. So here, if you read these little tiles, and I cropped this at these 12 tiles, you see a lot of astronomy related projects. So if there's a specific passion that you would like to pursue that really sits well with you and aligns with your interests, please take a little bit of time and you can peruse this website and find something that would fulfill you if you meaningfully contributed to the efforts. Now, the grand idea behind citizen science is that you have someone who's an expert in the field build this interface where we suffer from a human bottleneck, which means that there simply isn't enough professional astronomers to complete the task. And as I'll show in the remainder of this presentation, this may actually be a viable model because as of right now, with all the chat GPTs and other artificial intelligence powered engines, humans still outperform machines. I'm sure we'll build a Terminator soon enough, but we're not quite there yet. Every effort reaps rewards. What I'm showing you here is just a small selection of papers that have been published by the Pro-Am connection. So in red, all of these frames, these are co-authors that are citizen scientists that have contributed their time and effort through the citizen science projects. So you truly do have a lot of leeway because these are then peer-reviewed papers. And I'd imagine that publishing in a peer-reviewed paper, building your H-index and so on, is a pretty cool thing to do, even if you're not an astronomer. So I want to give you an example. I'm going to talk about planet hunters. I don't know how many people, let me ask this. Is anyone familiar with citizen science as a concept? About half of you. Okay. So is anyone familiar in particular with planet hunters? Okay, maybe a quarter of you. So planet hunters started with the Kepler mission. The idea was that we have about 150,000 stars that Kepler had observed essentially uninterruptedly. The duty cycle was about 92%. So we needed eyes on these light curves. The problem is that if you really truly want to make sure that you've not missed anything, putting a postdoc and coffee in one room and expecting that that'll do the trick just will not do. Kepler observed the same field uninterruptedly, essentially uninterruptedly for 4 years. Every 30 seconds, there was a snapshot. So you can imagine that if you're trying to find a needle in a haystack, you need a true concerted effort in order to do that. And this is how this project started with Kepler. The successor of that project is the TESS Planet Hunters Working Group that started under the lead of Nora Eisner, who's currently at the Flatiron Institute. And she was gracious enough to lend me some of her slides so that I can brag on her behalf what they've managed to accomplish. So this is what they're trying to do. The goal of Kepler, but even more so TESS, was to find an Earth-like planet around a sun-like star in a habitable zone. Of course, as a side effect, it'd be wonderful to collect all the planets that are out there. In fact, about 6,000 to date. But the Holy Grail, the pie in the sky, indeed remained to find an Earth-like planet revolving around a sun-like star in the habitable zone. I probably don't have to justify that goal, right? That's what we'd want to do. So these are so-called super Earths, and as you go down and down and down and down, here's our Earth, and that's what we are trying to explore. This is the domain. We want that planet to be rocky. That's why it has to be Earth-like. And ideally, we would like to see it have conditions to foster life. So this is the main drive behind this effort. And looking at our solar system, for example, you would think that our solar system's typical. Well, it turns out that no, it's really not. We have a single star, that's our sun. We have 8 planets, and then we have a whole bunch of dwarf planets like Pluto and Makemake, Ceres, Eris, and so on, and then everything else that I call debris on top of all the dust. So you can imagine if someone's looking at our solar system from someplace else, trying to figure that mess out, I would not like to be an astronomer on that planet. This is a difficult system. So the question is, what is it that's out there? What can we actually find? Now, let me demonstrate a problem. I'm pretty sure that everybody is familiar with the sizes in our own solar system. So if this over here is the sun, then that little blip there, a pinhead, would be Earth. And what we're trying to do is somehow detect that blip against this humongous radiating body. So it's going to be difficult to see it. I will show you an example where we actually can see it if the planet is large enough, but obviously for Earth-like planets, it is hopeless to do this with direct imaging. So instead, what we're trying to do is see these planets indirectly, which means we are trying to see a telltale sign of the presence of the planet without actually seeing the planet. So this is what it would look like if you can actually see it. Let me do this again. So what they've done here is they put a mask to mask out the corona of the star. And how many planets can you see? Huh? Try again. 4. Yeah, no, there's 4 planets. So let's do this again. See, 1, 2, 3, 4. There are your 4 planets. Everything else is noise, and this is not typical. It is difficult to see such a thing. And what you will be seeing in this case are the closest, well, not necessarily the closest in planets, but the largest planets that are in such a stellar system. The other possibility is to try to figure out the reflux motion due to the presence of a planet. This is called the radial velocity method. So the idea is that you cannot see the planet, but you can see that the star is wobbling. So when it's approaching you, its light will be moved towards the blue. And when it's receding from you, it'll move towards the red. You can measure this in spectral lines of the spectra. And from those spectral lines, you can then infer what the, at least minimal mass, would be of such an object. And if you find that the minimal mass is substellar, especially, for example, if on top of the radial velocities, you have information that the system is near edge on, you can actually work out the mass of such a planet. It is important to note here that you know thy planet only as far as you know thy star. So if you want to study the planet, you really need to know your star. And this is what that looks like. So I'm going to put a plug here because one of the world's most renowned spectroscopists happened to be sitting in this room. Right there, Ulisse Munari from Asiago Observatory. So if you ever want to know everything there is and then some, talk to Dr. Munari. He has been one of the champions of Echelle spectroscopy. He and my advisor are my PhD advisor are close collaborators, and they taught me everything I know about spectra. And I am up at about 0.1% of what Dr. Munari knows. So pick his brain about all these things. But what I did want to point out is that these black lines here, these are absorption lines, and that's what you hone in on. So you are looking for these shifts either towards the blue, that means something's coming towards you, or towards the red, that means something's going away from you. But what we're actually, whoa, this is a little bit garbled up. What we're actually trying to see is this. This is a genuine transit. Can you guess what's transiting what? This is Venus transiting the sun. So the hope is that this little blip going over the stellar surface will produce enough of a signal by blocking the light that we'll be able to measure it. So the logic is pretty simple. You have a planet that orbits the star, and if we are fortunate enough that the orbital plane of the planet coincides with our line of sight, you have lots of light, and then you go into the eclipse, and then you are eclipsing a part, you're going out, and then you are back to where you've been. This is, of course, highly idealized, but you get the picture. The problem is that planets such as Jupiter would exact about a 1% change. A planet such as Earth would exact a 0.01% change. That's 1 in 10,000. You probably see how this is a problem. Because when you're trying to see a planet this small around a star that may be as active as the sun and actually believe it, to not be fooled by either spots or flares or other surface phenomena that are happening on the sun, it's a tough job. So that's why you need so many eyes on these data. Because the more people look at the same data set, the better the chances that if something like this were to happen, we'll catch it. Whoop. So let me first give you a little bit of a showcase of what we'd found so that I whet your appetites a little bit, because all this stuff still lurks in the data. And I will also mention that everything that I'll show right now has been found by planet hunters, by citizen scientists. Not a single thing that I'll show right now has been found by professional astronomers. So we have rocky planets that are in several day orbits around their host stars. We call these lava worlds. You can imagine what Mercury looks like in our solar system. Now put it about 100 times closer, so that instead of 88 days, it's on, say, 8-hour orbit, give or take, or 1-day orbit. And you can imagine what a crazy, crazy whirlwind that would be. Do the exact same thing, but this time with a gaseous planet. And you get what we call hot Jupiters. Now, you should be scratching your heads and ask yourselves, how the heck did a planet such as Jupiter form so close to the star that it whizzes around in a matter of a few days? We know from our own solar system that there is such a clear divide between rocky planets that are inner planets, that are inside of the asteroid belt, and all the gaseous giants are on the outside. We understand that through invoking the nebular theory. The logic goes as this. When we had our primordial nebula that was contracting, all the material gravitated to one spot. That's where the sun is. The rest of the material, due to the conservation of angular momentum, started spinning around, and as it spun around, it formed the protoplanetary disk. And see, if you have a furnace in the center of that protoplanetary disk, what you'll do is you will evaporate all of the water and water compounds that are near the furnace, but they will not melt if you're far away from the furnace. So this is what we call the ice line or the water line. If you're on the other side of the ice line, you're building planets with way more Legos than you can on the inside of the snow line. So the basic idea is if you've evaporated the vast majority of your Legos, you only have rock and metals to play with, so you're building small rocky planets. But on the other side, you can build large gaseous planets because you have so many Legos to build them out of. But how do you then explain these hot Jupiters? Why would they survive? Why would these be any different? They actually cannot be any different. They had to have formed on the outskirts of such systems, and through scattering and dynamical interactions, they would have migrated inwards. And now, due to the selection effect, because they are easy to find, that's why we find so many of them. In fact, all of the planets, if I do not account and correct for the selection effect, the vast majority are hot Jupiters and hot Neptunes. But this is what we want. We want to find super Earths. And I just want to give you an idea. If this little circle here is Earth, then the green one would be super Earth, because everything else is already giants. These would be ice giants. This is the size of Saturn. That would be the size of Jupiter. So this hopefully gives you an idea that it is not quite trivial to find these planets. Now, another, I would argue, one of the most fascinating systems that planet hunters had found is K2-138. That means it's discovered by the Kepler-2 mission, the successor of Kepler. And people had converted that to music. Now, I actually do have a link and I'd show you, but my suggestion is that you Google K2-138. And if you do that, just find it. It's a first hit on YouTube. And once you have the time, I'm not going to play it here because we're not hooked to the sound in the room. So do take a look at that. I think both Beethoven and Pythagoras would be extremely happy. This is a perfect resonance system. And if you play this, it really sounds like a symphony. So do yourselves a favor, and if you do find it, bookmark it, and then you can play it for yourselves. And then, of course, are my favorites. These are circumbinary planets. As Katerina so kindly introduced me, you guys probably know that my actual passion are binary stars. And to find a planet around a binary star, oof, what could be better? So from the very first discovery of Kepler-16, which was our very first circumbinary planet that we discovered and published, we'd found quite a few lurking in the TESS data. And again, as I mentioned before, this had been found by a planet hunter. So let me give you a bit of statistics of how we're doing. This is a little bit dated since the beginning of this year, but the number now is 5,600 altogether. So here on the right, I break down by the discovery of an exoplanet by method. So I talked about transit and I talked about radial velocity method. Imaging I mentioned, and microlensing I kind of swept under the rug, because even though planets can be discovered, they can't really be characterized. So in my mind, yes, it is a detection technique, but not really a analysis, or I'll say the exploration technique. And if you look at the sizes of the stars, you see here that terrestrial, of course, are very, very low in terms of discoverability for the exact reasons that I've been mentioning before. Now, this little kid is quite a game changer because it covers the whole sky. So you might have seen this already. This is the Transiting Exoplanet Survey Satellite, known as TESS. It has a humongous field of view. The 4 cameras are working in unison. Each single camera is 24 by 24 degrees of arc, and 4 cameras line up like this so that it covers 96 degrees altogether. And this over here is what we call one sector of TESS observations. So once you have the first sector, every 27 days, TESS rotates its field of view until it completes 13 sectors per hemisphere. Then it flips and it does the exact same thing on the other side of the ecliptic plane. Here, marked in orange, are the so-called continuous viewing zones. Because of the overlap, we have uninterrupted data for a full year from those regions. So that allows us to look for planets that have longer orbital periods, especially those that are similar to Earth. So how do we do this? This is a light curve. I'm almost positive that everybody's familiar with light curves. So what you're plotting is the amount of light that you receive as a function of time. And so if you have a longer time series, for example, something like that, you can see the repetition. And I'm showing with dashed lines here what the repetition might be. So what you do, you cut this up into segments, then you overlap these segments, first one, then the other, and boom, you get yourselves a phased light curve. A phased light curve boosts the signal. Once you have a boosted signal, you're able to see that from this transit, you can infer the properties of the planet. So where do we stand? What I'm showing you here is the distribution of planetary radii as a function of their orbital period. And you can see, for comparison, where our solar system planets are. So you see this bias, right? Because we are biased towards closer in planets, because we need them to transit, of course, we're populating the left-hand side of this graph, where different symbols are where we pulled the planets from. So in particular, in orange, you see all the Kepler planets. In magenta, you're seeing all the confirmed TESS planets. And then in blue, light blue, you're seeing all the candidates that we have. Now, look at this and look at that. So this line is the duration of one sector of TESS data. So you see that by continued observations, Kepler, because it had 4 years worth of data, absolutely blew this out of the water. Note also that the x-axis is in log scale. So what you're seeing here is that as of right now, this is from the first 2 years of TESS data, we are, of course, biased to shorter periods. And please remember this graph. Which brings me to introduce Planet Hunters. So if you want to explore Planet Hunters, you would go to planethunters.org. There, you could peruse whatever is on there already, or you can decide and you can join, generate an account, and join the fun. So here, I'm showing you how many eyes we've had on light curves since 2018, December 2018. So over 18 million classifications, nearly 30,000 registered volunteers. Show me a computer cluster or an army of postdocs or anything else that can do this. Machine learning does not come even close, and I'll show you that in just a little bit. This is how it's done. It's a simple user interface. The only thing you need to do is if you see something that looks like a little transit, you just flag it and you click done. On top of that, you can communicate with others on this. There's a paper trail on everything that's done. And you can imagine if you have tens of thousands of people looking at light curves, quite a few are bound to look at the same light curve. And then if you think, hey, this may be a planet, you put a comment, hey, this is exciting, might be a planet. So the interface is very simple. It is intuitive. And what your contributions are at that point is to try to figure out whether the data tell you something that is interesting. There's a primer that you can do, like a tutorial, that teaches you how to recognize both real bona fide signal or how to recognize that something might be a false positive. Come on. Can you advance the slides for me, please? Ah, there we go. So, as I told you, in the first 2 years of Planet Hunter's efforts, over 200 new confirmed planets that were missed by automated searches were found by the Planet Hunters. That is huge. So let me show you where they are. Remember the radius period plot that I showed you just a couple minutes ago and asked to remember? That's what it is. Only right now, I'm showing you here two more things. All single transits where we've only had one single transit, so we don't quite know what the orbital period is, hence large error bars in the x direction. And then I'm showing you multi-transits where we can really pin down the orbital period. And this, for example, is how you can find a planet. What I'm showing you here are multiple sectors of data, and you can see the blip right here and right here. And these come in succession of 84 days. That helps you recognize that this indeed is something that recurs and is a planet candidate. All the volunteers that have flagged this and discussed this are written down here. And of course, this led to the publication of this first test object of interest. That's what TOI stands for. And then the number is the consecutive number. And this is what it looks like if you phase that up. This is a tiny, tiny, tiny signal. Remember that I told you 1 in 10,000 that you have to get to find an Earth? Well, look at the depth of what this is. So at 84-day period, the host stars slightly evolved, old, but you can detect signals like this in the data. And here are the co-authors on the discovery paper. There's another one, TOI 2319. I'm showing you the exact same data as before, but without breaking it down little by little. And I want to show you that you can do another thing. If you measure exactly at what time your transits happen, and you observe that they sometimes happen either a little bit early or a little bit late, you can plot that up. This is called eclipse timing variation. So when you're looking at eclipse timing, you're putting time again on the x-axis and the deviation from the expected arrival time on the y-axis. And if you're seeing more things than just one, this indicates that something is tugging on your system. And this way, you can discover non-transiting planets as well. In this particular case, 2 such planets that have been discovered, you guessed it, by planet hunters. And again, the final example that I have for you is the circumbinary planet that has been discovered with a planet that's 7 Earth radii, so quite small in the grand scheme of things, around 2 stars rather than 1. If you happen to not care about exoplanets, don't be disappointed. Planet hunters are singularly largest contributors of eclipsing binary detections as well. The TESS eclipsing binary paper that was published in 2022 also contained the systems that have been found by planet hunters, and we also included them as co-authors, of course. And here are the light curves, stellar light curves that you're seeing. So I just want to highlight one, which is a compact hierarchical triple star system. Its light curve looks something like this. So you see that you have 2 periodicities here. You have these big dips, and then you have the little separations among everything else. And so these two, the small one and the large one, correspond to a binary star and a third star that's in hierarchical configuration with the binary. Again, you look at the eclipse timing variations that I was just mentioning, and you're looking at radial velocities that tell you how those spectral lines are shifting to the blue or to the red. And from that, you can get an entire dynamical description of this system. So you get the orientations, the inclinations, everything that you need simply by solving the full, what we call a photodynamical model. And funnily enough, the inner pair is the fast eclipsing pair, and the other star is actually more massive than the sum of both of the other stars. And this is what we learn by solving a photodynamical model. And of course, publications ensued. What I'm showing you here are snapshots from the Planet Hunters website where you can talk to people. So there are discussion forums that when you see something crazy like this, you can actually shoot your hypotheses of what this might be and talk to like thinking people to try to figure out what this is. It is really wonderful to solve these puzzles. So if you enjoy escape rooms in real life, there are virtual escape rooms here that are just as addictive as the ones out there. So to conclude this, I want to remind you that the pro-am connection does not end at citizen science, but instead, there are many other ways where we professional astronomers crucially depend on people who are passionate about astronomy. The first one is those who are really committed and equip their houses or local hills with observatories. We always need follow-up observations. Of course, as I say here, the prerequisite is that you have observing facilities. These are usually expensive. You need to maintain them. You need to calibrate them. So it takes a bit of effort. Data interpretation and modeling is the next step. So if you find yourselves physically and mathematically inclined, we build tools to be intuitive for everybody. So hop on that bandwagon and try to help us solve these objects. One area where we really need your help is disseminating results to the general audience. You speak the lingo, believe it or not, better than we do. And because of that, and because you know more than the general audience, you are perfect science communicators that really could help get the entire community excited about astronomy and about astronomical discoveries. And finally, we can all work on maintaining constructive and supportive discourse with the public. Being in America, you may think that this is isolated to America, but the deep skepticism towards science is a result of populism everywhere. So when people come to me and say, nah, vaccines cause autism, they won't listen to scientific arguments. They are convinced that they think that vaccines cause autism and that that is enough because modern culture teaches them that their opinion is more important than facts. It is our job to reverse that. And who better to help than science enthusiasts such as yourselves? With this, I would like to conclude, say that being an astrophysicist has been an awesome thing. I'll stop here and answer any questions. Thank you.
Do you have any questions or comments? Ondra?
Andrej?
Okay, so from Andrej to Andrej. So the planet hunters that you showed and many other activities on the website that you showed in the beginning basically use amateur astronomers as sort of cheap neural networks, right? So right, like to go above that was basically just on your last slide, and in our group in this country, most people are interested in taking their own observations. So a lot of the discussions is that I already have the setup. So what do I observe to have maximum impact? So maybe if you can comment on that.
Absolutely. The biggest downside of the missions that I mentioned right now is that they observe in white light, single passband white light, which makes it difficult to infer temperatures of the stars. So chromatic observations are of utmost importance to truly deciphering these systems. As I mentioned before, if you are into planets, know thy star, then you'll know your planet. Same if you have a binary star. It's always important to know what the temperatures of individual stars are. If you have a single white passband, you will get the temperature ratio, but you will not get individual temperatures. You will have to either fall back onto some reported temperature in SIMBAD or 2MASS or input catalogs, but you will not be able to measure it. You want to contribute? Observe this system in eclipse and out of eclipse, just a couple of times. That in multiple passbands. That will give us the information we need to really anchor down the temperature. So that is one of the most obvious things. The other obvious thing is if you see that we have a sector's worth of data and only a single transit, help us find the next one. If the level of precision of your instrumentation can carry such observations, help us find it. The final thing that comes to mind when trying to observe things is when we have a large data set of continuously observed stars that professional astronomers may not have their eyes on, you're not only contributing to, for example, determining the orbital period, but to finding higher order multiples. From the eclipse timing variations, you see how much we can do. And where better to say that than here, where we have one of the biggest and most influential catalogs of eclipse timing variations right in Brno. So please contribute to such catalogs because that is what we need in order to truly decipher these systems. But Andrej, I have to say one thing. When we got Kepler data for the first time, I did precisely what I said that would be quite difficult. I got about 20 undergrad students in one room. I ordered something like 15 pizzas, and we went through 160,000 light curves in one day. We divided that up and we looked at each and every one and we flagged every single one that we possibly could flag. And on that one single night, we discovered more than 350 planets first before anybody else. That was then, of course, communicated back to the Kepler office, and those were tagged as Kepler objects of interest, so candidate planets. But the euphoria of my students having discovered a planet, you can imagine Facebook posts. Facebook was in at that time. So Facebook posts, what did I do today? Discovered 17 new exoplanets. It is awesome. So that is why I chose to talk about this. It is quite soul transforming to be a part of something as big as that.
Thank you very much. Any other questions? Pavel?
Thank you. Maybe I could elaborate a little bit more on a question from Andra, because in our society there are people passionate for real observation, for they have equipment and everything, and or want to start observing everything, and some of them are willing to find interesting objects for themselves, to do the effort to study things and so on. And but we have also members, other people do not have enough time, for instance, or they just want to spend night observing to have a good feeling about it, which is perfectly okay. And they need some resource to look at and what should I observe tonight without reading 20 papers prior. So is there any such resource or not?
We used to have it. We had two wonderful things, the IAU circulars and the IBVS, the Information Bulletin on Variable Stars. But maintaining those proved to be a Sisyphus task. It was very difficult. Honestly, I don't think that we have such resource available. I would love to be corrected because I sorely miss the same thing as well. Because when we want to do a summer project with a student, we scratch our heads and think, what might that be, right? To the best of my knowledge, and I really hope somebody corrects me, I don't think that we have something as easy as let me cherry pick something that would really contribute nicely to it. And I see that there's a comment all the way back there. So I'm really hopeful, really, really hopeful that Greg will correct me just now.
Yeah, so I'll just there are two things that I would say. One is the astronomical telegrams, ATEL, which anybody can subscribe to for free. That doesn't really have exoplanet stuff, but it has a lot of like novae and supernovae and things like that with coordinates and requests for observations, and you can observe. And there are contact information in the telegram for where you can send that to. And the other project is, you know, Łukasz Wyrzykowski?
Mhm.
Yeah. So he has the BH-TOM project, which is basically it's a sort of website data aggregator and data disseminator. And you can sign up to that again. And there are lists of targets that people would like to observe. You can observe them, and then you put in the data through the web page or through some Python script which uploads the data. And all you have to do is just do the basic reduction for flat field, dark bias, and then it will do the photometry automatically and everything. And then you will automatically be added to any paper that comes out with the results from that. And there have been, just like Andrej was showing earlier, the papers with all the amateur collaborators, they have the same thing. There's actually going to be a BH-TOM workshop in Crete in, I think, 2 weeks. And if I'm aware, I think Łukasz will be streaming it online. So you can join online and see how the project works. Or in any case, just look at the web page, BH Tom.
No, wonderful. Yet, if I can say, wouldn't it be wonderful if we had a website where professional astronomers would submit like a Amazon wish list cart. You don't put it in a cart, you put it on a wish list. And there's simply a list of things that we would love to do. Right off the top of my head, if such a website existed, I would be uploading stuff on there immediately. So maybe you're onto something. Maybe we need to have someone to champion that effort to build the infrastructure, the framework of such a website. And then I think many of us would jump on board.
Thank you. It was a great question.
Someone's already nominated, it seems.
Yeah, thank you. It was a great question and also great answers. And maybe the last one, please, Gintra.
It is just a comment. I thought Bill Borucki designed Kepler to find out the fraction of Earth-sized planets around solar-like stars in the habitable zone. Is that correct?
Yes. So the answer to that question is that every sun-like star has at least one Earth-like planet. When you correct for all the systematics, and can you repeat, please? No. I'm not. I'm flying at 7 a.m., unfortunately. But can you please repeat?
Do you want to?
Right.
Okay, thank you. I think time is over. So thank you very much, Andrej. It was great.